All right. So hi everybody. Thanks for joining this Victor class. So today we have the pleasure to have Grace Battle from NASA, GPL, the Jet Propulsion Lab in California, and Grace is gonna talk about SAR data and using remote sensing data for eruption response, but also monitoring, and you will be able to actually use some of these tools that we have available on Victor. Okay, so if you guys go into the short courses, so you go into the shared material Victor courses, and then spring 2025, you should see a new folder there called Week 12. And in there, you will see three files, including a notebook. So if you can copy and paste these into your home directory, and then open the README file, and copy and paste the command line that is on the README file. Let's say type copy conda install, and then some arguments there. And if you can copy that command line and then paste it into your terminal and run that command line. That's going to install some libraries and environment files for running the notebook, the Jupyter notebook. Yeah. So I can share quickly my screen just to show you guys how to do that. So yeah, so once you copy the three file into your directory, you have the Jupyter notebook here, you have a README file, and then you have a requirements.txt. So all you have to do is to copy that line here in your terminal.
Okay. So hi everyone. I'm Grace Pato. As Silvad said, I'm from JPL. I work under many projects at JPL, and one of them is under the ARIA, and the two of them are under the ARIA and the Opera projects at JPL. We provide remote sensing products really to the community, derive remote sensing products, and I'll be showing some of them as a demonstration towards this presentation. Yeah. So today I will talk about volcano geodesy and beyond, and the towards timely and accurate forecast of volcanic behavior using near or with near real-time analysis ready and GIS ready geodetic data sets. So the motivation of this work actually is based on, of course, this pressing need that we have to have this timely and accurate information to mitigate the societal impacts of geological hazards and potential cascading effects. And in volcanology, ideally, what we want to do is to be able to detect anomalous activity, monitor unrest, forecast how the future state of the volcanic system will evolve, and of course, be able to assess different what if impact scenarios that could affect society. And we want to do that in near real time or real time fashion. So, in figure here in the right side of the slide shows the ground deformation from these three plots here are ground plots of the ground deformation, the CO2, and the thermal, the thermal or the temperature, edifice temperature change for the Al volcano before the January 2020 eruption. You can see that these three data sets pretty much have this negative trend just before the eruption, and then it ramped up a year before the eruption, and it ramped up just before the January 2020 eruption. So what we want to do is be able to leverage such kind of data sets without the need to perform complex processing and analysis, so we can make core science-driven decision making. Okay. So as we know, as you already probably know about this, but just for a brief background on how volcanic system works. So of course everything starts deep into part of the earth, and magma migrates towards the shallower depths in the form of these melt packets or series of dike injection that so-called form these magma chambers or reservoirs. And so, as this chamber is continuously filled with magma, the pressure actually increases within the system, and we know that the ground inflates. So, an excess pressure, or typically we call it as the overpressure, can be generated if the chamber exceeds the lithostatic pressure or the pressure of the surrounding rock. So once the overpressure reaches this critical value, the magma chamber may rupture, and dike would be able to propagate. And if there is this sufficient pressure to drive the system, an eruption can occur. When the chamber ruptures, we know that the pressure can be released and the volcano deflates, such that some volcanoes have this inflation, deflation predictable behaviors. And I'll talk about this more later on, but it's more related to monitoring ground deformation on volcanoes. Currently, the challenge that we have is that for available data for everyone is that you have tons of variously collected data at different volcanoes for decades, but this data can also be sparse, both in space and time. Sometimes or most of the time lacks the spatio-temporal resolution, even with GNSS and INSAR. And I'm highlighting this because this is always the case that data processing before you'd be able to understand what's going on is that it requires tons of expertise and access to high-end, compute resources. Access to derived data or information can also be overwhelming for end users. Another challenge that we face when it comes to monitoring or understanding volcanic behavior is that we have these models, but these models are just representative of what is really happening. Right. And quoting George Box, which is very very famous in our world is or in our communities, like all models are wrong, and there is no one size that fits all model, and different models can sometimes explain the same observation. So as you can see here, so this is a simple two magma chamber that are stacked together. This is a model, modified model after Reverso. And this is another one which we call as this damage model, wherein this reservoir or upper part of the reservoir experiences damage through time. But these two models actually could be explained or could be represented by this kind of displacement time series. So there's some ambiguity on that. That's why. Most of the time, there's these three monitoring practices in volcanology. You have the gas monitoring, INSAR, or deformation monitoring through INSAR and GNSS, and there's the same seismicity. However, for this talk, I will focus on detecting and monitoring ground deformation, and that's because ground deformation is a powerful indicator of the long-term and short-term behavior of volcanoes. It has been used to detect precursors that are earlier than what volcanic gas and seismic monitoring can. It has a direct relationship to the subsurface pressurization, as I've explained earlier, and we can easily, or at least nowadays, easily measure ground deformation in several ways. But the most important techniques, again, are the GNSS and INSAR. With GNSS, of course, you can derive the three-dimensional displacement information at a point with daily to sub-daily temporal resolutions. And nowadays, at least for GNSS datasets, we have this high-level GNSS derived products that are available through many different repositories. One popular example is I'm showing here is the UNR, or University of Nevada, Reno's geodetic laboratories, one-stop shop of GPS data. That you can just go there, they even have an API. Click on a map, and then you'll get a time series of the deformation. So this is station GV04. This is in Sierra Negra. So how about INSAR obtaining the displacement data from INSAR? That's there are plenty of groups that have been providing displacement data nowadays, for example EGMS, but they're also kind of limited in geographic scope, I would say, and there's not a lot of routinely or near real-time processed displacement products that are provided anywhere else now. But before we go through the exercise, I just want to give a brief introduction or overview of INSAR, or basics of interferometry. So the INSAR has or SAR, each SAR images are formed when microwave signals emitted by the satellite are backscattered by the ground after it has been illuminated by a radar pulse, and each pixel in a radar image actually contains a complex number, and thus you have an amplitude and a phase component in each of the SAR data. As you can see here, this is an image or a SAR image from Sentinel-1 captured on January 9 and 2020. You can see that the amplitude component is very nice, but you don't have, just looking at the face at a date, you don't have any information that you can actually derive from here. So if you have another date, and there is a, at least two properly co-registered SAR that are taken at two distinct dates, and you have something that have occurred in between them, let's say a volcanic eruption, and then you take or cross multiply the phase component of it, you will get something like this, which is what we call as the INSAR or interferograms. So the principle of INSAR exploits the phase differences between the reference and the secondary images. And again, if there is this local surface deformation or displacement that occurred between these two acquisitions, you see this concentric pattern of fringes or concentric pattern of signals called as fringes. This one is, again, the 2020 eruption of Taal volcano in the Philippines. So the phase that you measure actually is not just the displacement. So there's a lot of like phase contribution or delay signal that are related to that signal that you have measured. There's a phase related to the orbital of the satellite, the topographic effects or changes, atmospheric effects, other sources of noise, and actually this is the deformation signal or the deformation phase that we always want to achieve. In practice, only, of course, the phase due to the ground displacement is important for us. We want to get that and correct or reduce in as much as possible those other signals. In cases where mapping of emplacement of lava flows and possibly quantifying the volume of erupted signals, you can try to derive this phase due to topography. Any questions so far from our audience? Okay, so the next slide actually is to be able to create this interferogram for the Mauna Loa eruption using CSLC datasets. I'm going to talk about CSLC later, but it's a product. The geocoded SLCs is a product or products from the Opera project. It's already co-registered and are geocoded, so it's very easy to use and calculate in order to obtain fringes and quantify, or in this case, map the newly emplaced lava flow. So if I go to this one, is it here? No, I have it in my local. Here. Okay. Okay, so this demonstration, you have the IPython notebook. There's just a bit of like introduction on what data sets are used here, but this is again the Opera CSLCS1 products. So to set up your environment, I hope you were able to do this. If not, I'll just walk you through the step by step. So the first part of this is just loading Python modules that are necessary to run the entire notebook, some plotting parameters or preferences, I would say, including this one. So this part is setting up your NASA credential or data login if you don't have a netrc file in your home directory. It will prompt you here. I have it already set up, so it will not basically ask me. So if I run this, actually, let's just run it. Okay, I'll just restart it. Okay, run that modules. Okay. So again, this will not, I will not be prompted because I already have my netrc in my lookup. So in this part, this is where users can intervene. For example, you can enter your site or AOI or volcano of interest. And the format is the west, southeast, north coordinates of your volcano of interest. This is actually I think this is somehow within the big island. Sometimes it's hard to kind of know where what are your lat longs, but a very good tip that I would tell you is to just go to ASF, for example, and then you can, where is this one? Okay, this is our site of interest. You can just do this thing and we'll give you this parameters. You can take this and then load it as a WKT um, um, line, or you can just take the min max of this one. But anyway, I already know what's my area of interest, so I just had to do this one. And I'm taking the descending track 87 in this case, and then I want to get the co-eruptive deformation related to the November 27, 2022 Mauna Loa eruption. So that's my first date or reference date, and then my secondary date is this one. I just have a saved directory.
Grace?
Yes.
How would users know the part number that they're interested in?
Path number. Oh, that's good. Good one. So can go here again in ASF. Then you can, so it's under dataset Sentinel-1. Okay, that was the Mauna Loa one. So November, I guess I want something that covers this one. 2022 December. Wait, say, did I put the right thing? December 5. Sorry. So, okay, that gives you tons of data set. That's not right. That's GRDH. What you want basically is the SLC. So you go, if I take it slowly, go to filters and then file type, go to SLC. Yeah, and then you can choose the direction, whatever you want. But I think this was the first co-eruptive interferogram, if I recall correctly. So in as much as possible, I want to get the earliest data set, right? To be able to check what's going on or how much did the ground deform as a result of the eruption. And I'll just click search on it, and then you'll have those passes. So I think this was first one, so it's covering. Okay, so I said it's the path 87 is here.
Okay.
Yeah, if you want to do the ascending case, just click on this one, on the ascending, or filter it out in this case. And then, it's much more cleaner, and then you'll be able to see it's path 1 to 4 for the ascending case.
Okay.
Yeah. So yeah, any questions about these parameters? You just need the orbit pass, the path number, and a reference and secondary dates. Then this part does everything for you to query and download the data sets that you need. I'll just click these functions. So this one is querying the database or the API of ASF DAC. And this is just getting the results and putting it in a GeoPandas data frame. So you have the geometries, all the metadata related to each of the SAR data set that you want. And what we want is to get only the relevant metadata. So I've just sorted it out in a way that I can easily read whatever I wanted. So I'm just taking the burst ID, file ID, start time, and the end time or stop, the URL of the data, of course, the geometry, this polygon inputs here, and the PG version. This is the processing version internally. There are unfortunately duplicates SLCs that are produced, so I would filter it to just this version. This is the latest one. And you'll end up having this data sets, of course. And we'll see what this data mean later when we show the map, which is coming up here now. So before you're gonna download the stuff, you're gonna be given this kind of map. What is really nice about the Opera SLCs is since it's burst-wise product, you can actually just pick the SLCs that are relevant for your case. Otherwise, if we go back here, you see that if you download the save file, this one here, it's 4 gigabytes and it has 27 bursts, and most of them are in the ocean, for example. So this is ascending, and it's the same case if I do the descending one. So it takes processing time and a lot of compute time for it. So that's one good thing about the Opera geocoded SLCs. You can just take the 3 bursts, and that's why it's very, very fast to just create the interferograms. So this is the part where I would download this 3 bursts, and for each burst I would have one reference and one secondary date that covers the eruption, or the start of the eruption. So this case, so I have the 1204 and then 1122. Okay, this is very quick because I have already downloaded it to my SLC folder. And here I'm just sorting the data frame. So now I have downloaded the data sets and I can read each of the SLCs, and then I want to stack them together for easier processing. So these functions take care of all the stacking and relevant cross multiplication that you need to be able to create the interferogram. So this part, can see this equation here. This is the equation for showing the amplitude. So the amplitude basically is the intensity. It's the yeah, it's the intensity or of the radar signal. So it's opening and reading it. It takes a couple of minutes to do that. But if we are impatient, we can go to the Zenodo version. Is it this one? Sorry. I think it's this one. Okay. Oh, I thought there's an overview for the Zenodo. Oh, there. Sorry. Oops. Yeah. Okay. That was the upload part. Okay. So if we want to see what will happen, it should be fast, but if we have, okay, now see, it's done. So it computes the amplitude for each of the SAR data. That's the top one, the middle part of the burst, and then the southern part of the burst that we computed, and that's for uh, the first or the reference date. And then same thing happens for the secondary dates for each of the bursts. This part 7 is where we generate the interferograms. If I go back to my slide here, it's basically cross multiplying the phase component so that we could basically computing for this to be able to get the fringes or retrieve the fringes. So this function is just making the colorful jet color for each of the fringe. This one, we will need this for the coherence, and I'm going to explain it later after this demonstration. This is the function where we calculate the interferograms. It's this part here that sorry, it's this part here. No, it's correct. It's this part here that I calculate the complex conjugate and divide it or normalize it with the amplitude. This function is simply a function to write the array into GeoTIFF file so you can load it in your favorite GIS platform or software. Okay. Just some bookkeeping. And now we will compute for the burst-wise interferogram first and then merge them together. So this, I'm pretty sure this will take some time because it needs to calculate for the complex conjugate. But if we go to the run results, which is in Zenodo, you will expect something like this for cross-multiplying November 22 and the December 4 SAR data sets. So, and then this is the corresponding coherence image for that interferogram. I'll explain the coherence in a short while. And again, for the middle burst, and then this is the coherence for the middle burst and the last part. Of course, you can extend your search area. I was just like focused on just getting the 3 fringes. You can extend it on getting the, the eastern fringe, eastern SAR images. Okay. So this part, or part A, is where the merging of this burst interferograms and the coherence happens, as well as saving these files to GeoTIFF. So you'll be able to do this later when you try the notebook out. But the results of the plot, or you should expect something like this, where you have this really nice merged fringes. Similar to the coherence, now you were able to map or show the coherence change between November 22 and December 5, and it's showing you the emplacement of the lava flow during the Mauna Loa eruption. Okay, any question before I move to the
Wait,
slide?
can you explain quickly how to read the interferogram for those who are not familiar with? So you got fringes, right? And the closer the fringes are close together, the more deformation there is, right? So one fringe is one phase of deformation, right?
Okay, yeah. So
You'll explain it better than me.
so let's go back to the figure here. Okay, so this is so the interferogram is negative pi to pi. It's a wrap phase, for example, and so it's kind of sometimes tricky to get an interpretation of it. It's best to always unwrap it, but the working equation is that the phase, I should have written it, is like this, and you have to unwrap the phase and then count the fringes, and it's half of the wavelength of the satellite for each fringe. So if you count, you have to count the number of fringes and then yeah, multiply it by the lambda over 2 to be able to get the displacement. But it's very tricky to do that, and the closer, or the um, the more fringes you have, it's a representative that the more deformation happens in that region. And typically, when we unwrap the face, when we count the fringes, so if you're unable, your eye can't even unwrap it or count anymore, you're it's basically too much fringes already, or it's like very dense fringe, and this is basically this area is experiencing fringe aliasing, meaning that it's saturated already in a way that you can measure the deformation, and that's because of the wavelength of the satellite. In this case, this is a C band, which is 5.6 centimeter. If you go to L band, which is around 12 centimeters, the fringes will be much how do you say, spaced. The contours are much spaced because it has a wavelength of 12 centimeters. Basically, if you have a ruler, you can measure more, right? If you have L band, and if you are in C band, you have like 5 centimeters of just a ruler. You have to do that in cycles. So if I go back to my slide here, okay. So you will be able to produce this two maps, but in SAR, again, I'll just say it again. Phase measurements are up between negative pi and pi. For example, here it's negative 3.14 to positive 3.14, and you have to convert this phase to discernible units. You unwrap it. So in 2D domain, so this is the phase cycle. This is what you actually see. These are the fringes in wrap phase, and the actual deformation is what we see as the absolute. You want to be able to achieve that or get that, model that. There are tools like the SNAFU. It's developed at Stanford. It's a statistical cost net workflow algorithm for phase unwrapping. It's what we use by default nowadays in the INSAR community, and it basically unwraps your phase. You will achieve something like this, but there's this sometimes offset between the absolute displacement and the unwrap value, and you can only achieve that or estimate that by doing inversion later on, or getting another set of interferogram, or using GPS. We model that when we do volcano deformation source modeling using MOGI, for example. We add that as a parameter to estimate the offset. Okay, so about the coherence, or the interferometric correlation. So coherence is the measure of the correlation of the phase information between the two SAR images, or in this case, two CSLC data. It is normally used as a qualitative marker of how good the interferogram is. The values normally ranges from 0, which is like black or dark color here, and 1, which is the bright ones. Bright pixels indicate regions of high coherence, meaning that before and after, when you did that interferometric or cross multiplication, before and after, the pixel remain coherent. And if there's a change in the scattering properties or acquisition geometry, and for example, in the case of the Mauna Loa eruption, there was a large amount of surface deformation and emplacement of the ground. It can lead to decorrelation, and then we can use the coherence to map the emplacement of the black flow. Because, typically, coherence also can be used to map damages when there's an earthquake, for example, and ruptures. So just for context, this is the coherence equation. So you have that cross multiplication of the first SLC and the second SLC. And this one, the bracket is the spatial average, and that's what I was showing earlier in this code. So that is the moving window mean. So basically, you take an n by n window, you average the pixel of your interferogram, and that's how you basically get it. And you normalize it with the intensity of the first SLC and the second SLC. This is the intensity or amplitude. Okay. So fortunately, you don't have to deal with this all the time. We now provide them almost routinely. We have two projects again at JPL where I'm involved: the ARIA project, the Advanced Rapid Imaging and Analysis project, and another one is Opera, or the Observational Products for End Users from Remote Sensing Analysis project. So ARIA is more of like an on-demand product. Its purpose is mostly related to research and disaster response, because we can tweak the parameters, we can respond quickly, we don't have operational constraints. It's primarily supported by research grants through NASA's program. And again, it's very agile to disaster response and scientific research. Opera, on the other hand, it's a project level funding with formal program requirements. So we don't have an urgent response requirement, but it's operationally produced. There's no operator that needs to trigger it. It goes to the NASA distributed archive, active archive center. So just more about this ARIA and Opera project. We both projects leverage AWS cloud based processing and the sources details, but yeah, all the production pipelines and codes that we develop are available through GitHub. Our data can be accessed through the Earth Data Search for Opera, and then also for disaster response, we have the ARIA Share portal. About the Opera project, so a bit more context about it. So NASA was funded to create these data products that actually directly address the needs of multiple US agencies that are determined. Actually, these satellite products are determined by every 2-year satellite needs working group survey. What we currently provide or produce are 3 or 4 products now: the surface displacement, the water or surface water extent disturbance, and then surface disturbance, and the vertical land motion later on. That will be a downstream product of the surface displacement. So basically a derived product. So remember that INSAR measures along the line of sight of the satellite. You can have a measurement along the ascending track, which is from south to north, and you can have a measurement from the descending track, which is north to south measurement. But you don't know you don't know the horizontal, you don't know the vertical information unless you convert it later on. But you always have to at least have 2 acquisition geometries. The line of sight measurement is again ambiguous. It contains three components: the east, north, and up component. And to be able to resolve that, problem, you need to at least normally have three data. It's in the inverse problem, but sometimes we assume that the north-south is 0 because of the flight direction. INSAR is very less sensitive to the north-south direction. So you can just take ascending and descending and then invert for the ground displacement later on. So there are much more Opera products that are now available to the DAC. These are the level 2 products. The one that I demonstrated is the CSLC, which is very raw product. If you want a full resolution interferogram, this is a 5 by 10 meter product. You want to use this one, but if you're in operational mode and you're a scientist just wants displacement, a line of sight displacement every now and then, and you don't want to do or deal with all the processing that I've shown you earlier, you just may want to wait for the displacement product, which is going to be released by next month. And then the VLM is way far in time. It's in 2028. So Opera will be implementing a geographical rollout of the historic processing for the displacement product, and will complete the historic processing by end of 2025. And that is including hopefully the Sentinel-1C, which is now operating along with Sentinel-1A. Unfortunately, Opera is only producing displacement products over the North America geographic scope. So you can see here it covers the entire, U.S. territories, mainland U.S. and U.S. territories, and some of up to Panama. I think it's up to Panama, and then in this border with Canada, it's U.S. plus 250 kilometers from the U.S. border. That's how we define our geographic scope. Okay. So to make your life again easier in the future, you'll just go to ASF and then click on this visualization portal, and then be able to download your point of interest, so you don't have to deal with all those processing in time, and it's a already high level product. So again, Opera is producing only North America displacement products. There is an Opera version, which is the EGMS in Europe, I think, and they're producing the same kind of product, but only covering Europe as well. So some of displacement Sentinel-1 products that we will produce from 2016 going forward. Here is an example of the Kilauea eruption. I can see this one is very nice, showing, just after the May 2018 eruption, slowly deflating. And then this one is Mount Edgecumbe, which suddenly became or reactivated around 2018, or between 2018 and 2019. We'll be able to have this kind of like continental scale ground deformation product, and you just go into that volcano of interest, pick your point, download the CSV, and be able to do your own modeling using these data sets. Just skip about ARIA. There's this part that I want to do for this demonstration, but I don't know if we have time, Sylvan. But this is to be able to get the line of sight velocity map and produce this displacement time series using ARIA GunW products for areas that are outside the North America geographic scope and European region. For example, you can ask or directly contact us, and then we'll produce the time series for you.
Yeah, we can try, yeah.
Okay. So I made made some kind of like notes on how to do that because it's more of like a CLI way of doing that. So we will put this in the Victor folder. Is it possible to do that? Yeah, I have it in my local at this point, Sylvan. But you can I can give this to you so you'll be able to distribute it later.
Yeah, I think what you can do is just do a demo, right? And then we can like get the files and then share them later for people to try.
Okay. So the first part would be installing Miniconda and installing ARIA tools, which is the main software or tool to get the ARIA GUN Ws. So for that case, we want to download Hawaii GUN Ws. GUN Ws are geocoded unwrapped interferograms. Why did I skip that information? So it's basically something like this. It's a standard displacement product provided by the ARIA project. As I've mentioned earlier, so ARIA is more of research and disaster response. So we have much flexibility in producing derived data sets, unlike Opera, which is very programmatic. It has a geographic scope, it has a fixed resolution and stuff like that. For most volcano observatories, it's outside our geographic scope, for example. Okay, so you can actually get the GUN Ws from ASF DAC. If we go again to this example of the Hawaii one, I can keep that area of interest, and then what I will change is only this part, data set. Then I'll go to ARIA S1 GUN W instead. And I want to measure the pre-eruptive displacement prior to the November 27 eruption. So I want to, for example, for this purposes, I just want to take the year of data from January to let's say November 27, right, is the eruption. So I want to get the time series for that one. And I think I want to check what is the deformation on the ascending track. You can do the descending, but the demo uses the ascending track for this case. Okay, and then I'll just update that. And it will show you all those interferograms that we've processed. You can see it's not fixed because of the Sentinel-1 SLC's Sentinel-1's way of acquiring the frames. It's moving in the azimuth direction, so it's not always fixed in time. So that was a major challenge in creating this interference or fixed frame. So you can have that, and you can see again, it's not, it's partially covered on the upper frame, and then you gotta stitch the southern frame to be able to get the entire Big Island. And if you download one of this, actually, let's see this one, November 25. You can download one, which is the one covering maybe the one. Well, let's see. If I download that one, actually, okay. And then I will go to QGIS. Where is my QGIS? Here. Okay. And what you can do, okay, sorry, I have tons of stuff in my QGIS. It's just drag and drop it in your layers, and you'll see something like this. So the NC file of ARIA GUN Ws has like many science grids that has ionospheric correction, like Verstrom, solid or tide correction, for example, troposphere, is empty for volcano products. We don't add the troposphere correction. You have the amplitude and the coherence, for example, and of course the unwrap phase, which is what you wanted to derive the displacement. There are the angles needed to transform the unwrap phase later on for modeling or for deriving the north, south, east, west, and up down component of the deformation. So you need those angles later on, but we'll not discuss it at this point. So if I just load those things here, and I just go to that layer. So you can see that's half of the interferogram, and I think what I'm showing is the unwrap phase, so we can modify the color. I just why can't I modify the color? It's strange. Yeah. Oh, it shows in another screen, that's why. I can just do that, and you'll have those kind of, that's the unwrap phase. You don't see the fringes anymore because the fringe again is the wrap phase. Now it's already unwrapped for you. You don't need to do anything else. So this one is, I think, the I'm showing is the coherence, and the other one is the amplitude. What you can do for the amplitude, since it's showing just black in here, you can just go here and then cumulative count. Normally it's what I do, and then you'll be able to show that. So it's pre-eruptive, so you don't see the emplacement of the lava flow. Okay, and then so you can download this one by one, but again, if we go back to the software that Arya already developed for you, is that you just need to install Arya tools, and then make your folders, set up your directories, and then just use this line script Arya download.py, what track you wanted, your bounding box, which is again west, east, and south and north. And then the version of the product that you wanted, 301 is our latest product. NT is the number of threads in parallel, if you want to do some parallel downloading. And then -S is the start of your start date of your data set, and then E is the end date of your data set. So again, I'm showing just between a year of eruption or less than a year of eruption. And then to set up the time series, so you can use MinPy for time series inversion to derive the velocity and get that points over in time. You gotta do just the ARIA-TS setup, and then just these parameters, where are your products or those NC files that you downloaded. Again, your bounding box. You can decrease the bounding box. It will crop the area for you if you just want to focus on Mauna Loa, for example, or Kilauea, because it covers Kilauea as well. And yeah, I downloaded the mask. It's a water mask. Again, the number of trends, which is NT. MO5, this is a funny trick, because we wanna be able to stitch these two frames, right? The northern and the southern frame, and we want to restrict the overlap between them. And I just gave I think it's 5 kilometer square area. It's something you can measure in QGIS. But yeah, if you don't put this minimum overlap, it will just get all those frames that are consistently there. So sometimes
the southern frame for this case can get like tossed out. So yeah, so this is an important parameter in my case when I stitch interferograms or frames that are overlapping. So that's just what you need to line scripts to set up your directory, all those things that you need to do the inversion. And if you want to learn more about the ARIA tools, we have a pretty much good documentation here. It's tons of information and more Jupyter Notebook tutorial as well. Okay, so MinPy is a software we use for time series inversions developed by Yunjun when he was a grad student in Miami. First part of this script or HTML is about installation, and again, the time series analysis is like starts from step 2, create your configuration file. In this repository, GitHub repository of MinPy, there are like many other templates that you can use if you're using ICE, Hype, or GMT-SAR, Snap. You can use it for any SBus time series processing to get your displacement product. For this one, I'm using ARIA product, and I'm just taking all those directories where I can get the unwrap file, the coherence file, the connected components, which is metric of the unwrapping, the DEM that they used or generated during the processing, incidence angle, azimuth angle, the mask, some computer configuration. I'm using a memory maximum of 64, local cluster, 8 parallelization or workers. And the default in MinPy is that it runs the tropospheric delay, but normally I turn it off for volcanic on purpose for volcanic studies. It's because any correction that you apply on a displacement product or interferogram and wrap phase can either sometimes just add noise, further noise to your data set. So I typically don't apply any correction because in any case, volcanoes are just a tiny footprint in the map. It's not always affected. Well, it's affected by troposphere a lot, but it can worsen or give you a misleading more displacement product. This part, adding correction requires really a lot of expertise and that. But yeah, so after you set up your config file, you just run small baseline app and then your config file, and then it does everything for you. And then we'll go to TS view just to show you how it works. I think I have it here already. I think. So this is the run results after I ran the small baseline app. And then if I just want to plot the results, for example, I just copy this one with some parameters. I reference it to this coordinate. This is the MKA GPS point, which is somewhere here. If I, oops, I have Conda activate MinPy. So don't forget that when you have your environment to just activate MinPy. And if I do this, I'll be able to show that. Okay. It's not showing. Okay, takes a while. So you have something like this, for example, and then you can plot. So that's the reference point, and then I'm plotting this one, and then you can scroll this, for example. That's the January or reference date, in this case, January 5, 2022. Then you can just scroll on that and see how the, interferograms or the unwrap phase is imaged. Yeah, and then you can hover over it, many points here. And you can even go to Kilauea, for example. Yeah, and it also produces the velocity file. So if you just want to use the velocity to be able to do some deformation analysis later on, you can look at the velocity here. So yeah, so it's around 10 to 15 cm per year during the that period, around 10, I think, of inflation. Yeah. And what's good about MinPy is that you can also save it as a GBs file. It's a MATLAB file, that mat file, using this line script here, and it should give you something like this, and you'll be able to directly use this for GBs. I don't know if everyone knows about GBs, but it's inversion software. Unfortunately, it's in MATLAB. It's developed by Marco Bagnardi and Andy. But yeah, it is a software that can invert for volcanic deformation and give you the source of or the source parameters for that displacement or deformation file that you ingest into the software. So it tells you what causes or what is the shape of the reservoir, what is the shape and length of the dike that triggered the eruption, for example. If I go to something like save, then I just hit tab. You have several things. You can save it as GDAL, as GMT file as well, as KMZ, QGIS, and ROIPAC file. So yeah, I think that's all for me for now, Sylvan. Did I miss something? Oh, sorry. I thought that I'm done. So if you have those displacement products, of course, you can do all those fancy things afterwards. The data set, this preparation, and creating the displacement time series, as you know, is tedious. And glad we now have systems or cloud-based systems like what we have at JPL, ARIA, and Opera projects that will just really distribute this derived products to the community so that you can just do your fancy machine learning analysis. Here, it's just some simple strategy that flags changes in the trend of a displacement data set. It gives volcano observatories like forecasting strategy, let's say like that, in a near real-time fashion. It just uses a 2 sigma standard deviation threshold. If the uncertainty goes beyond that, then it flags it as an anomaly. If you have a model dynamical model, you can do a model data fusion technique to sequentially track the next state of the system, do parameter estimation, and also track the sudden change in behavior. So in this case, you see that once this simulation was able to detect suddenly the change in the bottom inflow or the flux inflow into the magma reservoir. It's a simulation. I applied this in the past for the Sierra Negra interruptive period, showing overpressure changes as a result of varying influx Sierra Negra. just before the 2018 eruption. And yeah, just key takeaways. Timely information is crucial in mitigating the societal impacts of volcanic eruptions. And key ingredient to achieve this goal is access to this near real-time analysis-ready, GIS-ready data sets. Again, I sound like a broken record, but we now have projects that enables this science and applications with high resolution data sets, and so you can formulate your science-based decision making and framework through whatever advanced techniques that you can do with these data sets. Okay. And yeah, thanks everyone. Just exciting year for us. So yeah.
Yeah, thank you so much.
Yeah.
I just wanted to point out that on Victor, we have a in the workflows folder in the shared folder, something called dist Victor, like dist_Victor, which is a workflow that's just meant for everyone to kind of test out the disturbance like suite of Opera, and if you just copy and paste it, you do have to log in to your Earth Data account, but once you do that, it should be a very kind of painless process. You just specify a few values, and by the end you get a footprint more or less of an eruption that you chose. The one that we have implemented is the, I think, Iceland 2024 eruption, but you can change it to basically any other to get a footprint based on the disturbance suite. So this is kind of an adaptation of something that we that Grace and the team at LD worked on.
Oh, thanks for that, Sam. I didn't know you added that segmentation part. This is very nice. So yeah, you can try to run the notebook. This the dist Victor notebook that Sam was talking about, and you should be able to get this kind of lava flow map over Iceland.